Hi everyone, welcome to Om Learning Lab. In this video, we are going to understand the decoder side working in the transformer architecture in detail. Now in my previous videos, I have already explained in detail about the encoder section, about this particular chunk, how it works, how the inputs go into this, how they are processed, how the attention mechanism works, all of that. I have also covered briefly about positional encoding, why it is important, and also about multi-head attention, how that differs from the normal attention mechanism. Now, all said and done, once we have processed our input words through the attention mechanism, whatever outputs we have, we need to use it somehow in this decoder block. In this video, we are going to exactly understand how we do that. We'll first start by describing what exactly happens to the input embeddings that we get, and then we will see exactly how we utilize them. But before going there, that is the exact mechanism, the exact technicalities of how decoder works, I would like to give you some intuition, some practical intuition, so that the actual understanding or the actual logic behind why the given approach has been suggested in the paper and it worked so well, it's easy to understand, simply speaking. So what I want to tell here is, let's say you have a task wherein, let's say you have a table like this. Let's just skip this as it is. So the first picture is of course taken from the paper directly. People can of course see the second picture as well. This has been taken from the famous book Zuravsky NLP. I think it's available online, maintained by Stanford University. So fantastic book on NLP, and people are highly recommended to go through this as well if they're interested. But all said and done, you don't have to pay attention to this picture for now. I'll come to it later. So it's about a separate thing, which is masked multi-head attention mechanism mentioned in the decoder side. So that's another technical detail that I'll cover towards the end. Coming back to the topic, so let me just clear this up. This doesn't look good. So yeah, so let's just imagine that we have a huge table over here. It's a standard table which has some keys and some associated values with it. So this is key, this is value. And let's say this is regarding some sports articles, wherein key is something like the topic of the article and value is the entire article. So let's say there are some keys like Messi wins World Cup. So this is the title, and then you have entire text followed by it. Let's say that is one of the keys. Let's say some other keys like let's say it's from 2015 article, like there is this football club called Barcelona. Barcelona wins Champions League, wins UCL 2015. I think it was 15-16 season. I'm not sure. I don't remember. That's all right. I mean, the purpose is, this is the title, and we have the article associated with it. So we have the value here. So we have the article associated with it. Now, what we have is, we have a table which has a set of keys and values. The keys being the titles of any sports article, let's say, and the values the associated article. Now, let's say someone comes with us with a query, right? So the query is something like, let's say the query is about World Cup, Football World Cup 2022. So let's say the query is something like Football World Cup 2022. Now, of course, from these two given examples that we have, the more apt response that we should return is this article, right? Because it is regarding Football World Cup 2022. So definitely this is not much related with this particular article, which has the title Barcelona winning Champions League 2015-16. Rather, it's much more related to this title, which is Messi winning World Cup. I mean, Messi won World Cup 2022, right? So they are similar, so to speak. And so ideally, we should be returning this particular value. So in other words, if this is my Q query, this is my, so I should be able to do something like, for this particular query, I should search all these keys that I have. Let's say this is key 1, this is key 2, so on and so forth. Let's say I have n keys, and then I should be able to say that, you know what, this is the most similar key. So in vector format, we should take a dot product as usual, because if vectors are similar, then dot product scores are generally high. So that's the logic behind that. So you take dot products, and for people wondering about it, if we have two vectors like A and B, cos theta would be something like, mod A mod B cos theta is A dot B. So A vector dot B vector mod A mod B times cos theta. This is separate. This is A and B dot product. Now, for cos theta is a decreasing function usually, and if you want vectors to be close, theta should be as small as possible. If theta is as small as possible, then cos theta is as high as possible. In other words, this dot product should be as high as possible. Now, I am explaining this in point of view of cosine similarity. In reality, here we are simply taking dot product. We are not using cosine similarity, we are taking dot product. But I am explaining in terms of cosine similarity because it is easier to understand. So for example, let's say this is your vector space. You have some vector v1 here, and let's not call it v1, let's call it a only, and you have some vector p here, and you have some vector c here. So between a and c, this angle is more, let's call it some phi, and this angle is theta, right? So which of these two vectors are more similar? Definitely a and b are more similar. So if theta is less, it should be preferably as close as possible to 0. If that is the case, then cos theta will be high because it is a decreasing function in the first quadrant at least. So if that is the case, then this dot product should be as high as possible. So I am trying to give a sort of a reverse explanation, so to speak. But coming back to the topic, so if vectors are similar, then dot product is usually high. Let's not digress into this side details. I just wanted to give this for the sake of completeness. But anyways, so what we do is, for this particular query, we will scan all the keys that we have in the table, and we want to find that key which gives the highest, which is the most similar. So we take dot product with it, which is this one. And for that particular key, we will extract the value. Now, of course, if we want to extract the value, it will be something like, you had the query, you found the most similar matching key with it, and for that particular key, somehow you fetch its value, something like that. Now, something which is almost analogous to this basic concept is actually implemented in this paper. So that's what is happening here. If not exactly that, it's at least intuitively we can think of it as that, as the operations effectively trying to achieve that. So here we have our inputs, which will be like, the vectorized embedding of Henry and likes to play football. So there are 5 of these. So this will be sent as inputs. This will be our X matrix. We'll do all the attention process as we should. And let me represent the outputs in some other color. Let me not use this. Let me use red for these outputs. So let's say after the attention mechanism has been performed, these are the outputs. Remember that we will get a 5/3 output after after going through the entire attention mechanism. So people who are getting confused in what exactly happens in attention mechanism in encoder side, please go back and watch my videos. I will put the links to those videos in this description and in the end screen as well. So please be sure to check those out before continuing with this video. Now, of course, after we get all this from here, we will again project these attention embeddings into 2 matrices called key and value. So usually that is what we do. So when we have input embeddings, we project them into query, key and value matrices, and we do the entire math. So here, after all this process, we will just project them into 2 more matrices, just key and value. We will not be creating query matrix, please note. We'll just project them to key and value matrices. We can have some auxiliary weight matrices as we are doing WK, WV or whatever, and we'll try to project this into these two matrices, keys and values. Now, these two arrows that you see over here coming from the encoder side, these are the keys and the value matrices. In other words, imagine that through the attention mechanism, you are creating this table, right? What is this table of? This table basically tells you that here we had key as the article title and value as the entire article. So here you will have something like, what is a key? A key is basically all those words with which we compare the query, right? So that will be, in other words, what is that? When we are comparing the query to all these words, that's basically saying something like the exhaustive possibility that is present in our corpus. That is our key. And the value would refer to, if this is a particular key, which part should I pay most attention to? I mean, what was attention mechanism doing? So QK transpose divided by square root of DK multiplied with V, of course, after taking the softmax. This was effectively, this operation gives us a probability distribution that where we should pay the most attention to for a given query. And when we take the dot product with the value matrix, which is a projection of the original input embeddings, we just assign the weights, right? So we assign the relevant weights, that is, we have learned where we should pay more attention to, and that is being reflected in the values. So that's what we have here. So here the keys represent the same idea that it was before in the original attention mechanism. That is, it's effectively the entire corpus that we have, and the value is, it's basically the weighted, what can I say? I mean, it's basically a weighted combination of where we should pay the most attention to. Now, those two matrices will come from the encoder, and query will be taken directly from the output. Now, why that is important is, let's say, so for this particular input embedding, we had Henry likes to play football. The first output here ideally should be Henry, right? So if we have Henry here, let's say we can convert this Henry into some embedding as well. So of course, when we are generating some output, it will of course come in vector format, which is an embedding itself. Now what we'll do is, this is my query. So in other words, this Henry, this will be this. Just try to imagine, just try to draw an analogy between what is happening in transformer and this basic example. This is just for intuitive details. So exact things might not match, and it might be difficult for me also to explain. But try to draw the analogy in your mind that you have some output word, which is your query. What you do is, when you take the dot product with the keys, you are basically searching your entire corpus that, okay, so in my entire corpus, with what is this particular output matching the most? And then for that particular key, you return the corresponding value, which is like the weighted summation of it's basically the weighted summation of the attention weights, right? So whatever weights we have learned, the probabilistic distribution, so that is multiplied with the value matrix, and ultimately we return that basically after taking the dot product with value, that particular value would be highlighted, which will have the highest attention, right? So this is your query. You take the dot product with the keys, that operation basically will reflect which particular key was the most similar, and then you return the corresponding value. Just try to fit that into your head. I know it's kind of difficult to imagine it like that, but as far as I could tell, this is the only way we can intuitively try to understand why the operation has been done here the way it has been, and why it works this well, right? So again, coming back to the example, you have some word, try to find the most similar word. So QK transpose, softmax of it, that just finds it, because through attention mechanism, you already have generated these keys and value projections, right? You already have learned where you should pay the most attention to, and all the details you already know, you have learned a lot. And so based on that, you find the most relevant key and the most relevant value corresponding to it. So from here, this is giving the Q. This are your key, K and V, and this passes through the standard attention mechanism mentioned here. Please note that this particular block, multi-head attention, add a norm, feed forward, add a norm, this is basically the same thing. So I'll represent it in green or something. So this particular block, this block right here, and this part, these are effectively the same thing. What is changing is how we are bringing the query, key and value matrices. Key and value being generated from the encoder side. That is what we have learned from the given input matrices, from the given input embeddings. And the query is basically from the output. So based on the previous word, find the most similar word and its corresponding value, intuitively speaking. Because most likely that would be the next word to be output, right? And we have already learned all the attention, where it should pay more attention to. We have also given positional importance, everything we have taken care of. Just find the most similar, most relevant, and try to return it as the next output. Is as simple as that. I mean, logically speaking. So that being said, this remains to be explained. What is masked multi-head attention? So why is that important? That is one thing which is missing to be explained here. And once we have done the attention mechanism here, what is it that, and we have passed everything through feed-forward neural networks, how are you exactly going to get the outputs and how are you going to learn from it? So that is one thing that is still remaining to be explained. But before that, I want to just cover this particular part, which is masked multi-head attention. So what is masked multi-head attention? So basically, whenever you have some output word, so here we had just input embeddings and we were sending it through the encoder to perform attention on it. Similarly, whatever outputs we have, we will not just directly use them as a query. We'll actually do attention mechanism on them and then use the generated matrix as a query. Because just think about it, whatever the previous word was in a given language doesn't mean that that is the only thing which is important to predict the next word. I mean, whenever you look at any particular sentence, let's say Henry likes to, and then you want to predict this word play, all three are important, right? It's not just two. I explained using just a single word just for simplicity's purpose, but in real example, you need to pay attention to the entire sentence which is preceding, or in other words, the entire output that you have already seen. So for that, whatever output embeddings you have got, you have to pass each of them, like stack them in some X matrix, just as we are doing it for the encoder side, and do attention on them. And then whatever output you get, that is your query. Because it has all the information regarding what all we have seen so far. And then for that particular query, you find the relevant key from the encoder and the corresponding value. And you pass them through feed-forward neural network, you give the output, and then the model will learn. The important thing here is it is masked multi-head attention. It's not normal multi-head attention. And the difference is, to explain that, I'll come here to this picture taken from Zurovsky NLP. So what we're doing is, normally when we take Q times K transpose, it's basically every word in the sentence has access to all the other words in the given corpus. So for example, if I represent this sentence in a matrix and do Q times K transpose, this likes will also have access to all these three words, to, play and football, which come after it, right? But we don't want that in context of jobs where we have to predict the next word. So when we are predicting the next word, we want the model to learn that part, how to predict the next word. So we can't really afford to already tell the model that, you know what, if this, we can't afford to tell the model what the next word is, right? So I'll just explain it a bit more. So let's say that here in our input embedding, we had Henry likes to play football, and in output, so far I have got Henry, I don't know the pronunciation, I apologize, this is in French. So let's say I have got these three words. So far I have got these three words. Okay. Now what I'm saying is, when I have these three words, I'll stack them and I'll send them to do masked multi-thread attention to get the next query, and then it can go hit the key and value pair to generate this. I can't give Henry access to this or this, because if I do, I am indirectly teaching the model the next words, right? I am exposing the model to the next words. So that would be a sort of cheating, so to speak, because the whole purpose is to make sure that our model learns to predict the next word. So we can't afford to, tell the model that, what, this is the next word. We can't do that. Here it is okay. In the encoder side, that's okay, because you have the input sentence, and we are just trying to understand correlation between every word with the other, and also we are taking the ordering of the words into account. So in encoder section, it's all right because it is the input language sentence or the input sentence, and we just want to extract all information out of it. But in decoder side, we are using the output. We are using the output directly here. We are not using the input. When using the output, we need to be careful, because if we expose Henry to these two words, we are leaking output information. So in machine learning, we have some X data and some Y data. Y is, let's say, Y target, right? Okay. The model needs to learn this. And in testing, we'll have some X dash and Y test, right? So we'll train the model on this and we'll test on this. During training, we cannot expose this to the model, right? We want the model to learn some pattern using training data, and then using whatever generalized observation it made from the training data, we should be able to apply that to the test data. We cannot expose the model to the test data. That is cheating. Model already has all the information. So what kind of training are you doing? Right. So in the decoder side, specifically here, since we are using the output, we cannot afford to tell the model the next words that are present. Henry cannot have access to these two words. So in order to prevent that, what we do is, when we take QK transpose, this upper triangular matrix is set to -infinity. What that will do? So for query 1, you just have access to key 1. Key 1, in other words, the word itself. For query 2, you have access to K1 and K2. K1 and K2, please think about the previous videos. It will be the first two words. So the second query, of course, it needs to have the information about itself and the previous one. That's the one purpose, right? Because all the information preceding to it, including itself, are important. Similarly, query 3 will have access to the first word, second word, and the third word. Right? So on and so forth. That is why we're setting to -infinity, because when we take QKT transpose, we'll ultimately apply a softmax on this. So when you apply softmax, e to the power -infinity will just become 0. So ultimately it will become 0. When you try to take a dot product with V, that will just go down, right? This will just go down. Those values will not be considered. So effectively, we are ensuring that our model is not exposed to the output data. We are not cheating. The training process is proper, as rigorous as possible. So that's the purpose of masked attention mechanism, that we are not exposing futuristic data to the model. Because if you do so, then guessing the next word is not that challenging, right? You are basically, in a way, you are leaking data to the model. So that's erratic. So that's what we are ensuring by masked multi-thread attention mechanism. And again, going back to what we are doing, we use all the outputs that we generated, we'll do attention on it, and we'll generate a query matrix out of it, which is basically saying that, okay, so far, let's say we have seen 3 words so far. So the query matrix would say, you know what, I have this much information. Based on this much information, let me search the keys that I have learned in the encoder training part, and the corresponding value to it. Right? Of course, these are all in probabilistic distribution. For query key transpose will give a probabilistic distribution, and multiplication with V will effectively return that particular value. I mean, in the value matrix, those particular values will be highlighted, which had the highest probability. That's the whole purpose, where we should pay the highest attention to. So wherever we should pay the highest attention to, that will be highlighted, and feed that to the feed-forward neural network and get the next output. That's it. Now coming back to the last part, that how exactly how exactly the training happens. That let's say everything is done, right? So you had the query, you took K transpose multi dot product with V, and you got some output. You send it to the feed forward neural network. Then what? So this is basically what can I say? A neural network, a simple, fully connected neural network, which will transform the entire input into a vector called logits vector. Let me write it here. So this particular thing, this will transform this into something called a logits vector. Now what this logits vector is, let's say we are doing English to French translation, and in our French vocabulary, let's say just for example's sake, we had 7 words, let's say in total. So let's say we have word 1, word 2, word 3, word 4, word 5, word 6, and word 7. Of course, this is not a practical example. In practicality, our language will have billions of words, most probably, or whatever, how much ever the vocabulary exists. So this linear layer is a fully connected neural network that will transform the entire output that it got from the feed-forward neural network into a logits vector. This logits vector would have the dimension of the total vocabulary size, but this would effectively have scores on which we'll take softmax. So again, going back to what softmax is, let's say this had some values like 1, 2, 0.6, 5, 9, I don't know, 2, 4, whatever. So when we take softmax, of course, this is going to be highlighted, right? Word 5 will be highlighted. And when word 5 is highlighted, basically what you're saying is, you know what, maybe word 5 is the most likely output. So that will be the output here. Now, how model will learn? So for any machine learning algorithm, we have 4 steps for learning. We have a training set. Let's call this X, and we have Y target. And the first step is you create a hypothesis and try to learn. So here the hypothesis is entire attention mechanism, whichever is happening, and taking the output, embedding to generate query, using these keys and values from encoder to get the output, passing it through feed-forward neural network, then through the linear layer, which is basically a fully connected neural network, transforming the entire output it's getting from this part into a logits vector, and applying softmax on it, everything. So that is our hypothesis function. And from the hypothesis function, we'll get this is the first step. The second step would be to get a Y pred. So we'll generate Y prediction. The third step would be to take a difference, Y pred and Y target. We'll see how related or how different these two are. This will be computed based on the loss function that we have. So, and then the fourth step is you update the weights. So you go back and update whatever you have learned to the model. So here, of course, what is important is how we are generating these predictions, query, key and value predictions, how we are generating them. And in multi-head attention, how we are using this W0, which is for multi-head attention mechanism. Or if you are trying to learn positional encoding weights also, those also needs to be updated. So we'll keep on updating them as long as our Y pred and Y target are not similar, right? So in this particular example, if we have 7 words in the corpus, we'll have a vector of size 7 with some scores associated with that, and we'll take softmax to get the final probability. And in this case, of course, this particular word 5 has the highest probability. Let's say this was not this particular word. This should be the ideal output. Assuming that this is the output sentence we are sending into the decoder part currently. So let's say it was something like football instead of AU. So our model will learn that, right? So we'll come to the third part, which is Y pred minus Y target. So far, whatever we have seen, this is just the first 2 parts, right? We have a hypothesis, which is the entire model. We do a prediction, which is this part, this softmax computation. Then we do the back propagation mechanism in short, which is compute how much different these are. And based on that, you update the weights. There are multiple methods to do that. You calculate the gradients and all that stuff, and you update the weights. You keep on updating the weights. You keep on repeating this process again and again, as long as you don't get good results, a greatly performing model. So that would be all for this video. I know this must have been a handful, and I am 100% sure that the first 2 videos would be much more easier to understand than this particular video. In fact, as the concepts keep going on, it becomes more and more difficult to understand. So first we start with the encoder side, what is happening when we have some inputs. That video would be the easiest to understand, at least intuitively, what is happening. Then the next video is about multi-head attention and positional encoding. There it becomes a bit more vague to understand what is happening intuitively, although I tried to make it understandable as much as possible based on how much my understanding was. And then the final one, that is, oh, okay, we have the encoder side. What exactly are we trying to achieve through the decoder side? How exactly is this architecture so powerful? So that is also kind of difficult to understand. So that's why I took this simple example of key value table and a query. And based on the query, you try to match with the key. Based on the similar key, you fetch the value. So, and I try to explain that when you take dot products, the higher the dot product is, the more similarities. I try to explain that in a reverse explanation manner using cosine similarity. That is, in cosine similarity, if theta is less, cos theta is more. And it's more basically in the RHS you have dot product, right? So that just implies that dot product has to be more. That's in the numerator. So here we're taking dot product, not cosine similarity, but regardless, what we'll do is we'll use all the outputs that we have obtained to generate the query, this particular queue in red, and we'll do that by passing the entire output through masked multi-head attention, because we don't want to expose the model to futuristic outputs. That would be a sort of cheating. Model is already exposed to the output that it should predict. That's not the correct way. So we do masked multi-head attention and we get the particular query. For that particular query or the particular output information we have so far, Q is basically output information we have so far. You search the keys that we have learned through the encoder and you get the particular value output for it. Of course, that would be a weight distribution multiplied with the value vector, with the particular value which we should pay most attention to being highlighted. That's the whole purpose of attention mechanism anyways. You pass it through feed-forward layers, and then the linear layer would output a logit vector which has the size of the vocabulary, and it would have some scores, and then you take softmax to get the probability distribution. Highest probability word would be your output or your y pred. Then you compute the loss between y target and y pred. So for this case, this would be your y target. This is your y pred. So you compute the loss between two, and then you update all your weights, all your projection matrices, all your matrices that you need to for performing multi-head attention, all the weights that you have, all your hyperparameters. I think these are parameters, not hyperparameters. These are parameters, right? I mean to say the weights and biases. Yeah, you update the parameters, and you keep on doing that as long as your model doesn't perform well. So that would be in a nutshell. It's not in a nutshell. It's actually quite elaborate. I tried to explain as much as possible. So that would be how the decoder side works. If anyone knows a more intuitive or a more better way, so to speak, to explain how this decoder side works, please feel free to comment that in the comment section. Or if you have some relevant video somewhere, you can also link that in the comment section. I would be more than happy to learn myself, and I would be even more happier if my viewers get to learn in a better fashion. So having said that, thanks everyone who have followed these 3 videos so far. I hope I was able to give you some idea regarding some intuitive idea as well as some mathematical idea regarding why the attention mechanism as it has been used in this transformer model architecture is so powerful and it has worked so well. Of course, there have been some changes here and there in subsequent research papers. That is quite expected, but the base transformer model was revolutionary in itself, which is this particular architecture in your screen right now. And I have been able to give some idea why it was so powerful and why it worked so well, because intuitively speaking, like the entire paper, the entire architecture is based on intuition. I mean, how we think about things, right? So you have a text, you try to find where you should pay the most attention to, take into account the order of the words as well, the grammar of the word as well. And then based on the output, you try to fetch what you have learned. Go back to your table, find that particular value, and then you learn from it. So you try to preserve as much information as possible. That's the whole idea. So I hope these videos have been helpful. Thanks again for watching all these videos. Consider liking and subscribing to my channel if you find them helpful. So see you in the next one. Bye.